All right, so in this chapter, well, it's called static equilibrium, but that's only half the chapter. Okay, so we'll study two things. We'll study static equilibrium plus elasticity. Okay. Yep.
The test next week, or not yet?
I don't know. How many chapters? Well, what? Yeah. 13 is a long chapter. Yeah. All right, so this chapter actually contains two things, static equilibrium and elasticity. Equilibrium means A equal to 0. You do not have any acceleration. Okay. If your acceleration is 0, does that mean you're at rest? No. So that's why you have this. Okay, so static means your velocity is 0. Yeah. So if your velocity is not 0, then that's dynamic equilibrium. Yeah. Just this half of the chapter will become a whole course in your junior level. And it's a fairly hard course. And that's just, that course is called statics. Okay. And that is just two equations. This equation and this equation. Yeah. If you want to be technically correct. What does this equation tell you? What is this equation saying?
If you add all the forces, they add up to 0.
Right. So the sum of all the forces acting on an object should be 0 if you want static equilibrium. And what is this saying? The sum of all the torques that these forces exert on the object must be 0. Okay. So for an object, an extended object to be in static equilibrium, these two conditions be met. Okay. And that'll be the entire course. Okay, so that's the first half of this course. And we'll come to elasticity. Okay. Okay. So here's an extended object, this bone, and there are several forces acting on it. The weight of this bowling ball, the tension in this muscle, and the reaction force of this bone on that bone. Okay, so if this bone is to be at rest, the sum of these three forces should be 0. Well, and the weight of the bone itself. The sum of all those forces should be 0, and the sum of the torques of these forces must be 0. Okay. So now let me show you why you need these two conditions. Okay, so we'll use a simple example. Yeah. I apply a force like this to this object. That's the center of mass of the object. What will happen to this object? It will accelerate upward. Okay? So it will accelerate in that direction. Yeah. Now, nothing. It'll remain at rest. Okay. How about now? Nothing. All right, so it'll remain at rest. Okay. As long as all the forces acting go through the center of mass, then the only condition you need for equilibrium is this. Okay. Now, for extended objects, when the forces acting do not go through the center of mass. So, for instance, I'll take the same guy. Now, what will happen? It will rotate. Okay, so this condition is still satisfied, but it's not in equilibrium. What you need to make sure is that the sum of the torques is also 0 for extended objects. Yep. So you need two conditions to make it to make sure that the object will be in equilibrium. So now, can you tell me where would I need to apply this force to ensure that it's in equilibrium?
You need the second one going
Okay, so
right and up.
how about now? Now the sum of the forces are 0 and the sum of the torques are 0 as well. And now it will be in equilibrium. Okay? So those are the two conditions you need for static equilibrium. And that's what the first chapter is about. Okay? Now, first part of the chapter is about. Okay, so now before we do that, we will define center of gravity. Okay, we want to define center of gravity because that's where the force of gravity acts. Okay. So now before I do this, so we had talked about center of mass. So let's say this is a square and it's a square plate and it has uniform density. Where is the center of mass of this object? In the center of it. Okay. There is the center of mass. Okay. So if this were Earth, and that's the uniform plate. So if it's a small plate, the center of gravity is at the same place. But let's say if this were a plate, metal plate, and it was huge. Huge meaning something like the size of Mount Everest. Then the center of gravity would be there. Slightly closer to the Earth. Okay? So only for very, very large objects will the center of gravity be different than the center of mass. Okay? And we'll probably not be building such structures, but we'll still learn what the center of gravity. Yes?
Why is it?
Because what is the acceleration due to gravity? Huh? No, what is the value of the acceleration due to gravity? 9.8. It's 9.8, oops. It's 9.8 meters per second squared here. It's 9.6 meters per second squared here. So only for objects whose acceleration, where the acceleration due to gravity changes over the dimension of the object, will center of gravity be different. Okay?
It's got pretty big.
Yep. Mount Everest is big. So it's got to be large. What does large mean? So large means large. It has to be comparable to the radius of the Earth. And the radius of the Earth is 4,000 miles or 6,400 kilometers. So even Mount Everest is not that big. 64 kilometers is 1% of the radius of the Earth. So you have to have an object about 100 kilometers big before you start noticing it. Okay? All right. So here's the definition, just again. So as far as we're concerned, center of gravity and center of mass will essentially be the same, okay? The points will not be very different. But if you had a very, very large object, okay, the acceleration due to gravity, okay. So if the acceleration due to gravity is different along different points, then the center of gravity is defined. So this was the center of mass formula, and the center of gravity formula is exactly the same, except that the you put acceleration due to gravity at those locations, okay, divided by that. And now if the object is small enough where all those values are the same, equal to g, then g will cancel and this will be exactly equal to that. Yep. So the center of gravity is different than the center of mass only when the acceleration due to gravity changes over the size of the object. Yep. The reason we want to define the center of gravity is because that's where the force of gravity acts. Yep. And you just saw that for extended objects where forces are acting at different locations, the two conditions for static equilibrium are those forces should add up to 0, and the torques of those forces should add up to 0. And so that's why we are talking about all of this. Yep. So here's just a pretty picture. Do you notice anything pretty about it? What's that?
The top piece is hanging all the way out.
Very good. So you see this guy is hanging off the edge. And you can do this. So this was at Harvard University, and they were pretty proud of it. See that? All right, so it's hanging out the edge, and look at that. So you can even turn it. And this is not just silly stuff. Oh yeah, there it is. There. That's the computer science building, Boston University. Okay, so you can build buildings like that. Yeah. All right, so what's going on? All right, so for this guy to balance, the top guy to balance, his center of mass needs to be above his footprint. Okay, so that guy, so here's the top guy, there's the top guy, his center of mass is there, and his center of mass needs to be above his footprint. There's his footprint. Okay, so if the center of mass is right of that edge, then that guy would topple over. Okay, so all you got to do is make sure that his center of mass is behind there. Okay, now you have to do the same thing for each set. So for these two guys, for the top two tiles, their center of mass is there. For the top two tiles, there's the center of mass, and that is behind this edge. For the top three guys, there's the center of mass, and that's behind the edge. Yep. And so you can keep doing that. Yeah. You already saw this. Again, the center of mass of this guy has to be above this footprint. Get to balance. Okay, so conditions for equilibrium for an extended object, you saw that. For an extended object, just the fact that sum of the forces equal to 0 is not good enough. So for instance, this is not in equilibrium. What you need is this additional condition for when forces are acting on an extended object. Okay, that the sum of the torques of these forces should be 0 as well for equilibrium. Okay, so why are we interested in that? So, for instance, in our life, you have structures like this. You have varying forces acting on this structure, and you don't want this structure moving or falling down. Okay, so you want this to be in equilibrium, and we'll come to that. Okay, so for instance, this guy walking on this on the plank, he doesn't want this scaffold to move. Okay, so at all times he wants this to be in static equilibrium. Okay. All right, so we want to analyze situations like this. So those are the two conditions, and like I said, these two equations will be the basis for an entire course. Okay, so you will be analyzing things like this. Okay, structures like this, and you want these structures to remain in equilibrium no matter where he stands. Okay. All right, so we will keep things simple, and all the forces acting, we'll only consider situations where all the forces acting are in a plane. Okay, so then these will be two-dimensional forces, so that's two equations. Okay, and then this will be in the third dimension, the torque of those forces. So if this is in the xy plane, the torque will be in the z direction. Okay, so those are three equations. When you get to your statics course, of course, this will be three-dimensional, and that will be three-dimensional as well. Again, so then stuff will get more complicated. By the way, so this is sort of do all these penguins weigh the same? No? All right, so just like in a seesaw, okay, the further out you are, the lighter you need to be to balance. So if you have just two guys, here's a big fella and a little fella, lighter fella further out gives you the same torque. Okay, so just like that. So let's say this is x, this is 3x, and this would be m, this would be 3m. Okay, so now this. So if this is m, this would be 3m. Now so the center of mass is right there. The center of mass of this system is right there. So this is 4m. 4m times 3x is 12. This would be 12m. Okay, and that's 12 times 3x. This guy would be 36m. So this is sort of misleading. This diagram is very misleading. If this penguin has a mass m, this guy is 36 times as heavy. Okay. And you guys will see, I mean, I'm sure you guys have seen sculptures like this in all kinds of places. Okay. So there is physics that goes into that. Okay. Anyway, we'll consider two-dimensional forces. Yeah. Did you guys understand how that thing worked? What this was this was providing a clockwise torque about this point, and this guy has to provide a counterclockwise torque. So 3m times x should equal m times 3x. Okay, and so on. And so this was 4m. 4m times 3x should provide 12m times x counterclockwise. Okay. All right, so for our two-dimensional forces, this is a two-dimensional vector, and that's in the third dimension. So the sum of the x components of the forces should add up to 0. Sum of the y components of the forces should add up to 0. And the torque should add up to 0. Okay, so this is the kind of stuff we'll be interested in. We'll be interested in static equilibrium problems. So you have a scaffold here. Here's an extended object. and there will be several forces acting on this object. So for instance, the weight of the scaffold itself, this fellow standing on it, there's a tension of the string acting on it. And are there any other forces acting on this object? Hmm? What normal force? Well, the normal force is exerted by the scaffold on him. So we are interested only in the forces acting on the scaffold. Okay, what is happening is this scaffold is being pushed against the wall, and the wall reacts against it. Okay? So here are the forces acting on the scaffold. What we are interested in is that the scaffold not move. Okay, so what this diagram shows you is here's the scaffold, here's the tension on the scaffold. So the rope or the cable is pulling on the scaffold with that force in that direction. Here's the weight of the guy, here's the weight of the scaffold itself. The scaffold is being pushed against the wall, and the wall is pushing back on the scaffold. There's the reaction force. So here's a free body diagram. The free body diagram shows you the objects and only the essential things, which are the forces. So those are the four forces. What is it that you want? That the scaffold not move, or at least that's what this guy wants. Okay? And if this is not to move, what should be true? That the sum of all these forces should be 0. And since it's an extended object and all these forces are not going through the center of mass, the additional condition, so if all those forces were like this, if those forces were like this, that they were all going through the center of mass, then all you would need is this condition. But since they were not going through the center of mass, you need this additional condition as well. Okay, so the sum of the torque should be 0. Now, when you calculate the torques of these forces, the torques will depend upon what point you calculate the torques about. So you can calculate the torque about this point, or you can calculate the torque about this point. Did you guys understand that? How many points can you calculate the torque about? Infinite. So here's the deal. So which point do you calculate the torque about?
Center of gravity?
Okay, so here's the thing. Okay. So first thing, if the sum of the torques are 0, then you can calculate the torque about any point and it won't matter. Okay. What point do you want to calculate about? So let's say in your problem you don't want to solve for this guy. Then what do? You calculate the torques about that point and that guy is eliminated. Okay. So if you want to eliminate a force and you don't want to be bothered about calculating that, so you calculate the torques about that point. Okay. So that's how you choose it. Since if the sum of the torques about as one point is 0, then the sum of the torques about every other point will be 0. Okay? And so you want to be smart about the choice of the point about which you're going to calculate the torque. All right, so keep that in mind. Okay. Okay. So let me state this again. For extended objects, when all forces do not go through the center of mass, the two conditions for equilibrium are the sum of the forces should be 0 and the sum of the torques of these forces should be 0. Okay? And this is the basis for the entire course, statics. Okay, so what have we done in going from there to there? we've replaced this force by its x and y component. We replace this force by its x and y components. Okay, so this is entirely equivalent to that. Okay, so you can replace this by these two actual forces and this by these two actual forces. Okay, and it'll be the same. Why did we do that? So let's say we calculate the torque about this point. These two guys will have zero torque. This guy will have zero torque. Only this guy will have a torque. This guy will have a torque. This guy will have a torque. Okay? So we did it for convenience. So when net torque is zero, the choice of axis is arbitrary. Okay? Or the choice of the point about which you calculate the torque is arbitrary. A force that acts along a line passing through the axis produces zero torque. So if this is the point about which you're calculating the torque, about which you're calculating, this guy will have zero torque because his moment arm is zero. This guy will have zero torque. This guy will have zero torque, and so on. Okay, so let me show you something interesting about this so you can. Here's your arm. Let's say you're holding a bowling ball. Well, how much does a bowling ball weigh? 15 pounds, okay. So let's say 15 pounds. Okay, and now I'm going to guess some numbers. Okay, so let's say this distance is roughly about your arm, which is about 20 inches. Okay. And this is about 2 inches. Okay. And so we're calculating the torques about this point. This mass times 20 inches, that's the moment arm. That's a clockwise torque. And the tension in the muscle, okay, that's a counterclockwise torque. That's 2 inches. Okay. So, and again, you can, so tension times 2 inches minus clockwise torques are 15 pounds times 20 inches. Or we can say mg. So the tension in your muscles is 10 times mg. So to lift a mass, your muscles are applying a force 10 times the weight of the object. Sounds like a pretty bad design to me. Right? Why is that? Hmm?
Isn't it like feedback related? You don't want to apply it.
Okay, so this is why it's designed that way. For this guy, and this is in a small approximation, when this guy moves 10 inches, this guy has to move only 1 inches. Your muscles they won't contract too much. And so that's why the design is that. Okay, so since you can't contract too much, you put up with having to apply large forces. Okay, the idea is the following. Work done is force times the distance. And if you want the force to move a small distance, you have to apply a large force. Okay, so that's the idea. All right. So again, what we want to learn is, so here is a complicated looking situation. This is the free body diagram. So you want to be able to just write down the essential parts. So there is the arm, there is the weight, there is the bowling ball, There's the reaction force. This should actually be here. And there's the tension in the muscle. So the three forces acting on this arm are 1, 2, 3. Okay? And then we apply those two conditions for it. Okay. All right, so here's another extended object. Okay, the wall, so this is a smooth wall. So it only exerts a normal force. If there was friction in the wall, then this is going to try and slide this way. If there was friction, then there would be a static friction force there. Okay? So when you get to your junior level and so on classes, you will deal with that kind of stuff. But for right now, we are not going to deal with that. So this is a smooth wall, and there's the normal force. Okay?
I think the screens are trying to catch up right now.
Is it just happening now?
It's just repeating what we did.
We just
Oh, this is crazy. What?
Like it already showed all this, and now it's showing it again, but faster. I don't know why.
I guess that problem has reappeared, huh? Okay, let me know when it stops. All right. So this is a smooth wall, and the only force it can exert is the normal force. So again, all we're going to draw is the essential things. So here's the ladder, and let's put Eli on the ladder. Okay. Okay. So now we'll add Eli's weight. Okay, as Eli is climbing up, what does he hope? The ladder doesn't slip. Not he, the ladder doesn't. All right. All right, so here are all the forces acting on the ladder. There's his weight, the weight of the ladder. And if it slipped, the foot of the ladder would want to move in that direction. And so you need a static friction force in that direction. Okay. So here are all the forces, and for Eli's health sake, we want this to be true. Okay? All right. So to make sure that this doesn't slip, that's where you'll see the rubber boot on your ladders. Okay? All right, so you calculate it that way. Okay, so the normal force will be equal to the weight of the ladder plus this. The static friction force is equal to the this force, the wall pushing back, and so on. All right, so what I'm going to do is I'm just going to briefly mention elasticity. I'll have to come back to this. I don't have enough time to finish this portion. Okay, so here's, so as a material scientist and a civil engineer, this will concern you. Okay, so here's the deal. So let's say you're driving on the bridge. What happens to the cables when you get on the bridge? What's that?
They get pulled down.
When you add weight, these cables will stretch. Okay? And when the weight goes away, what do you want for the cable to do?
Just go back to the original state.
To go back to the original state. How many times? Infinitely many, right? Ideally, as many times as possible. You want your structures to exhibit elastic behavior. Okay? So when you stress them, they deform. And when the stress is removed, you want the deformation to go back to zero. Okay, that is elastic behavior. And you see this in rubber bands. You stretch a rubber band, and then let go of the rubber band, it goes back. But of course, in a rubber band, you can do this a finite number of times, and it'll snap eventually. You let the rubber band, you throw the rubber band outside in the sunlight, it gets brittle. It won't last an infinite number of times. Okay? So weathering changes the elastic behavior of an object. Okay? All right, so when I apply a stress, what happens? So this is a blown up version of that. Okay, so this is the microscopic view. When this stretched, what happened to the atoms?
A little further apart.
They all went further apart. Okay, so this guy moved over here, this guy moved over here, this guy moved over here. How much did they stretch? When did they know how to stop?
Whenever they were balanced, the added force.
Right, very good. So we modeled the atoms with springs. When this guy moved in that direction, what happened? There's a force pulling him back. Okay, so I'm going to just draw. I'm going to draw this many atoms. This guy is being pulled back. This guy is being pulled back. This guy is being pulled back. This guy. Okay. All those forces need to add up to that big force that was pulled. That's how they decide how much to stretch. Okay? All right, so when you apply a stress to an object, there is a strain. Okay, so every object experiences a strain, that is, it deforms. When you remove the stress, the strain goes away. Okay? And what you want is for your structures to behave elastically. Meaning behave elastically. What do we mean by behaving elastically? When you remove the stress, you want it to go back to its original size. When you drive away, you don't want this cable to lengthen just a little bit. Okay? Because then the next guy drives by, it stretches a little more. Before long, your bridge won't be there, but it'll be there. And you don't want that. Okay? So you want elastic behavior. Okay? So there will be three kinds of deformations that we'll talk about. Okay. When this is called tensile stress, when you're increasing the length of the object. So the predominant dimension is the length, which is changing. That's what's noticeable. Is there any other dimension that is changing? I'm sorry? I'm sorry?
The width.
What's happening to the width?
Shrinking.
I'm sorry?
Shrinking.
It's shrinking. The volume of this object doesn't change. So when the length decreased, the area of cross-section decreased. But that's not as noticeable because that dimension is small. Okay? So we'll consider tensile stress, where the most noticeable deformation is in the length. We'll consider volume stresses. This is bulk stresses, where you're applying forces perpendicular to the object and the volume is decreasing. Okay, so we'll be concerned about this. For instance, let's say you are designing a submarine, and here's a window, so you can charge people money to be able to see outside. Now, the stress of the hull is different than the bulk moduli properties of the window. Okay, so you've got to build leak-proof windows. Okay, so bulk modulus is when you're applying volume stresses. Okay, and here is another shearing stress that you apply. So if you apply forces like that, this layer will move relative to that layer. And that's actually how you cut or use scissors. That's what the scissors are doing. This guy is applying a force in that direction. This guy is applying a force in this direction. And the center layer cleaves. That's how you cut objects. Okay. So we'll apply tensile stresses. We'll apply bulk stresses. And we'll apply shearing stresses. And what is it that we want when we remove the stresses? We want the object to go back to its original shape. Okay. So we'll talk about that